Everybody online can hear me? I'll take that as a yes. All right, so let me just quickly walk through the a couple of changes I made to the code from last class. I think I posted something about it maybe a half hour after class last time. Our logic was actually fine all along. We were wondering why it was printing out multiple times. It's because, as you suggested, we weren't jumping ahead in the string. So I would say, hey, go process, the next array, which is fine. But when we came back to the previous one, it was still going. That's why it ended up processing the array multiple times, because we got to it different times. So what I did is a kind of a step in the middle, because this ultimately isn't what we're going to be doing. What we're ultimately going to be doing is turning this into objects, not into, outputted strings. Go ahead. Are you recording? Yeah, thank you. So we'll be transitioning towards building objects of a JSON array or a JSON object today, which will have its own name value pairs housed in it, that kind of stuff. But for right now, we wrote a couple of functions. We have process JSON object, which process JSON object is kind of our starting point. It says, hey, if I'm looking at an opening square bracket, this is actually a JSON array. So go ahead and deal with it as a JSON array. Otherwise, it must start with an opening curly brace. So we use the same logic as we did last time, where we're counting the number of curly braces. We go through from the next bucket all the way potentially to the end. And each time through, notice I'm returning a string, and we're going to be able to use this today. This is the string of the thing we just captured. All right, so my job here is to build up a string. So I start temp off with the empty string. I have found one opening curly brace so far. I go from the next bucket potentially to the end of the string. If I'm looking at another opening curly brace, I do tack something onto temp because I'm building up a string to respond. Somewhat unimportant right this exact second, but I'll tack on to temp this guy, then I'll go ahead and process that JSON object. Starting, so here's my whole string, but then I also am passing in my starting point. Where should you start looking in this guy? So I pass in the starting point, which is my current value of I, and I catch in answer the rest of that JSON object that this guy is built for doing. So I tack it on here. But then this is the thing we didn't have last time, is I force I to jump ahead. Say, look, I just captured, the next 11 characters, let's say. That was the contents of our JSON object. No problem. From this guy's perspective now, he can skip past those 11 characters and pick up after that JSON object, because I now have that JSON object. All right, so this is what we were not doing last time. All right, so still incrementing my curly braces. And keep in mind, this process JSON object is actually calling this function again, passing it my entire JSON string, but I'm changing the starting location. Maybe I'm saying start processing this JSON object starting at bucket 9, something like that. And then he goes and does exactly what he did before, but the original call here said start at bucket 0. And then what I do is, once it comes back here with, hey, here's the string that I just printed, you'll see that down here. When I find the corresponding closing curly brace, what do? I print out temp, which should have my answer in it, and then I go ahead and return that string. So if I go ahead and run this, just so you can see what that looks like. So this is like the value of temp. This is the value of temp so on and so forth. So I'm printing it out, but then I'm returning it. So when I return it, it's getting stored inside of answer right here. Answer has a length, and that's the value that I'm adding to my current value of I to jump me forward in that string from this guy's perspective to keep processing the rest of this JSON string after the part that I just processed. Okay, so in our output here, we should see our individual parts. This is the first JSON array we ran into, this guy. This is that first JSON object we ran into, this guy. This is the second JSON object we ran into, this guy. And then this is my initial call, which captures that entire JSON object. Make sense? Okay, so now we're picking up the correct strings, let's say, out of this guy. Now, ultimately, what we want to do, though, is we want to say, well, this guy's a JSON array. What's a JSON array? It's a collection of JSON values, let's say, where a JSON value can be a JSON object or a JSON array. All right, well, so for us, our object for JSON array should have a collection type in it. We need to collect some things. All right. Similarly, if we have a, now for us right now, let's just say the things that we're collecting in here are JSON objects. Now, if we look at our JSON object, this guy is a collection of name value pairs, which could be another object, right? So we can have something called a name value pair, where the name is a string and the value is something that is of type JSON value. For JSON object, we want to use that as our starting point. So, you know, we have a string is equal to some value, where the value can be a string, it could be an int, it could be a double, it could be a JSON object, it could be a JSON array, anything that is of legal JSON value type. Okay, but this guy here is a collection of name value pairs. This guy here is a collection of JSON values. Make sense? The difference between those two? All right, so now we need to have the ability to hold collections of things. Now, if I give you a random JSON string, do we necessarily know ahead of time what the collection size is going to be? Do we know that this guy is 3 name value pairs where this guy was only 2 name value pairs? We have to be flexible, right? We need to be able to handle an elastic number of name value pairs. All right, so with that in mind, go back here to the notes. We have several different abstract data types that we talk about in this class. And the first one is something called a linear linked list. So actually, I'm going to just put it after this guy. I might bump into it. Actually, I probably do bump into it here. This is fine. This picture works. All right. So now most of our modern languages do have some of these things built into them. It's a common type that we might use. We're going to write our own, at least initially. So in Python, you guys are already used to using the list. There is a set thing. There's a stack in there. There's dictionaries. C++, we have the standard template library, which gives us vectors, lists, queues, stacks, sets, maps. Java, we have, you know, the collection generic type. We have sets, we have lists, we have linked lists, maps, queues. We've used array lists in Java, which are kind of an abstract data type, a traditional one, but actually it's implemented on top of arrays, which can be a little memory inefficient, but who cares? It's not our problem. That's however they implemented it is how they implemented it. But for us in here, we're focused more on the algorithm aspect of it and how do we implement those abstract data types ourselves. And then we're going to apply our abstract data type to this collection of objects that we're going to be building. All right, so the first thing we're going to look at is this idea of a list abstract data type. I usually refer to these guys as linear linked lists, singly linked lists. Now, the reason I say linear is this guy's all in one row, right? We have an element followed by another element, followed by another element, followed by another element. It's a line. It's linear, it's a list, as opposed to a non-linear, which would be like a tree. I probably used to have a picture of a tree somewhere in here. I don't yet. But a tree would have a node, then maybe a couple children, and then that guy has a couple children, i.e. not linear. Okay? So initially, we're going to be focused on this idea of a linear linked list. Now, if we were to mention, let's see, do I do it here? I don't necessarily, so let me just do this slide. Let's call this a singly linked list versus an array. And we've already talked about this stuff with arrays. So arrays are stored in contiguous memory. This translates into they are relatively fast and relatively memory inefficient. Okay, that's the highlight reel for and low light reel for arrays. Linked lists are not stored in contiguous memory, and I'll actually go ahead and throw something in here for arrays. Must set the max size at the beginning. So linear linked lists are not stored in contiguous memory. These guys are relatively slow, and they are relatively memory efficient. We don't have to set the max size at the beginning. A linked list can grow and shrink arbitrarily. So if we need to add something else, we can add something else. If we need to remove something, we can remove something. And it just changes the footprint of the memory we're dealing with. So here's that picture of it where, you know, we have the idea of the head of a list, the beginning of a list. We also might keep track of the end of the list. Maybe we're interested in getting, if we're going to add something to the end of our collection, we think about our linked list as a collection. If we want to add something to the end of that, maybe it's easiest to go ahead and just jump to the last element on there and then tack a new thing on. If we want to add something before the beginning of the beginning of the list, we go to the head, and then we maybe create the new thing and make it point to the same thing head points to. And we're using pointers a lot here. So the idea here is that this object, maybe we call this guy a node. This object keeps track of the value it holds as well as a pointer to the next node. Where is the next guy in memory? All right. So if we were designing a linked list, we would say we have the idea of a node object, where a node has a value. So maybe initially we're going to create our sample linked list as a collection of integers. And then we're going to be moving on where maybe it's a collection of Hearthstone cards. Okay. But initially it'll have maybe an int. A lot of times this is called the payload. Okay, so this is the value that this node holds. And then it also has a node pointer, next node. This holds the memory address where the next node in the list lives, or null if it is the end of the list. So back to this picture, this guy has a payload of 4 and has a next node that points to this guy, who has a payload of 6, who has a next node that points to this guy, who has a payload of 8, who has a next node that points to this guy, who has a payload of 2, who has a next node that points to null. This is the current end of the list. Now, since we're dealing with memory locations, now presumably, I'll just make up some numbers. Maybe this guy's in memory location 100, this guy's in memory location 400, this is in 450, this is in 700. They are not right next to each other in contiguous memory because we created these node objects as we needed them. So initially we created an empty linked list, and an empty linked list is something that has a head and a tail, let's say. Might be handy to keep track of both of those. So we come in here, if I go ahead and say a linked list has a node pointer called head. This points to the first element in the list, or null for the empty list, and a null pointer tail. This points to the last, actually, instead of node, say the last node in the list, or null for the empty list. Okay, so that might be what's inside of our linked list. Now, we might want to have a couple of quality of life type things. So maybe we're also interested in the current count, the number of elements currently in our list. Is 0 for the empty list. Because sometimes we want to know, does this list have anything in it? We might ask, get its count, get its size, get its length, however you want to, whatever you want that function to be called. But ultimately, we're going to keep track of the number of elements that are in this list. Whenever we add something, the count goes up. Whenever we remove something, the count goes down. Okay, so the linked list object itself is pretty simple. I know where the beginning of the list is, I know where the end of the list is, and I know how many things are in the list. All right, make some sense? Each element in this list is one of these dudes, where it holds a value, that's the payload that lives there, and then it also holds a pointer to the next dude in the list. So if we want to walk through a list, if I want to get to value 8 here, if this was an array, this is at bucket 0, bucket 1, bucket 2, I would go to the base address of this guy, then take 2 integer size steps, or in this case, 2 node size steps to get to this 8, this value 8. Because I'm assuming they're right next to each other in memory. They're stored in contiguous memory. With linked lists, we cannot make that assumption. And this goes back to the statement right here. Linked lists, they're relatively slow for the reason we're talking about right here. We have to traverse through memory. We have to hopscotch from the first element to the second element to the third element to finally get to someplace because they are not right next to each other in memory. I can't just say I want the third element, no problem. I'll run to the beginning of the list and I'll just take one big leap to get to the third element through memory because it's just right down the street. It's right over there. I just have to take a big hop. All right. Where in this case, I can't necessarily assume that the values are next to each other. They might be, right? We might just get lucky when we ask the operating system for some memory. It might happen to hand us out addresses that are next to each other, but there's no guarantee of that. So I say these guys are relatively slow because if I want to get to this 8, I have to start by visiting this guy here. Then I say, okay, well, who are you attached to? Where's the next guy after you? So I'll follow this link here to get to the next node. Then I'll follow this link here to get to the next node. Now I've arrived at bucket 2 in this case. Okay, but I had to go to bucket 0 and bucket 1 first. I had to visit those locations in memory to follow the yellow brick road to my final destination. Make sense? So we're going to say that's relatively slow because of the number of stops. But the good news is computers are pretty fast, so who cares? All right. Most of the time, we're not going to care. The benefit we're getting from this is that because we didn't have to reserve a whole bunch of memory in a row, I can now say, well, initially I'm holding nothing. Then I'm going to hold one thing. So I'll just have one little link, one little place in memory. Then I want to hold another thing, create another place in memory, make that guy attached to him. So I don't need these giant blocks of land. I only need the exact amount of memory I'm currently using, and I can add values without destroying. In order for me to add this 6, I didn't have to destroy the 4. I could just say, well, let's create the 6, and we'll just make the 4 know about where the 6 is. When I create the 8, I didn't have to control the destroy the 4 or the 6. I just made the 8, taught the 6 how to point to the next guy. Make sense? So we're going to say this is relatively memory efficient, but it also, because of this, gives us the ability to represent arbitrary size collections. I can have 0 elements in it. I can have 5 elements in it. I can have 3 elements in it. And I'm being a good steward of using memory while doing that, because the only thing, when I remove something, the only thing I'm doing is destroying memory related to a single node. Whenever I'm adding something, I'm creating memory related to a single node and then remembering where that memory lives by attaching it to the previous guy. All right, make some sense? All right, so we're going to go ahead and start writing a linked list, and then we're going to think about what are some common functions we might want to add to a linked list. And keep in mind, we're building a collection, and collections' jobs are to hold things, right? Right now, the things that we're holding, I'm just going to call generically a node, and the payload of that node is kind of what dictates the value that we're holding. And right now, we're going to do this with integers so that our focus can be on linked lists, and then we'll upgrade it to be able to hold our deck of Hearthstone cards, right? Okay, so let's go back over here to our code. With the collection, we might say that the obvious things we definitely need are like add something to the collection, get something from the collection, maybe remove something from the collection if we want to have the, but we can just decide that we always add to the end, we always remove to the end, we always add to the front, or always remove from the front. We can decide how we want it to, we probably have multiple ways of adding. We can add to the front, we can add to the end, we can add somewhere in the middle if we wanted to. And we're going to explore each of those over the next couple of classes. But ultimately, we're giving the functionality to this collection that we need to store a collection of things. So I'm going to go into my code here. And I'm going to keep this all in this Hearthstone game online thing for right now. So I'm going to kind of steal my starting point for a header file here. I'm going to create a new header file. We're going to call this guy node HPP. We're creating a class here called node. We decided a node is going to have an int payload. We also decided that a node would have a node pointer next node. We will have a constructor for our node that takes in the thing it's going to hold, right? Then we're also going to go ahead and have a way of setting this guy's next node. So void set next node is equal to a node pointer n. And we'll see how these guys grow here in a second. All right, so that's kind of our prototype for our interface for what nodes will look like. All right, so now let's go and implement our class node. So I'll create a node.cpp, and we will include node.hpp. And then here's the couple of functions we need to write here. So we'll have node that guy, node that guy. All All right, so this is where we're actually implementing them. When we create a node, initially with the payload, what do? We set this guy's payload equal to the payload that was passed in. And then we'll also go ahead and specifically set this guy's next node equal to, I think it's NULL, like that, for the null value in C++. All right, similarly, to set the next node, I'm going to go ahead and say this dot next node is equal to whatever node you passed in, the pointer to that node. We probably also want to be able to get the next node so we can traverse it, right? If we go back to our picture here, if I go ahead and start at head, and I say, is this the value I'm looking for? Let's just say it's not. Then I need to get this guy's next node so that I can point to this guy. All right, but now when let's say my list looked like this, just the 4, and I'm adding another node to it, I would need to set this guy's next node equal to the pointer that is this guy. All right, so I need to be able to get next nodes. I need to be able to set next nodes. I probably also need to be able to get payloads. I might be interested in the value that lives at a node, right? And right now, that guy is private. So I would need to give myself a getter for that. So let's go ahead and give myself a node pointer, get next node, and then also an int, get payload. So we'll add 2 more functions to our interface, and then we'll go and implement those functions. Get next node, he's just going to return this next node. I need to put this dude on there. This is what attaches it to that header file. I'm implementing something that I interfaced or I prototyped inside of the header file. So get next node just says return the value of next node, which is a private member of node HPP. That's why I need to have a function that is a public. Notice this guy is in the public collection of things. So all these guys are public functions. They would have, since they're inside the class node, they have access to the private members of node. But to externally give somebody access to the payload, I need to do it through a read-only method, a getter. Okay. So get next node just returns the next node. Get payload will return this payload. So we're going to say that's a node for a starting point. Okay. So a node's able to be created with a value. We can set the next node to make it point to another place. We can get the next node to find out where it points. And then we can get the payload to get the value at that location. All right, next. And again, I'll steal my starting point for the header. And I actually did not need to use string here, right? Which means I also didn't need to use namespace standard. All right, so we're going to go ahead. We're going to create another file. We're going to call this guy LinkedList.hpp. All right, we're going to create a class called LinkedList. And we're going to have a public section. Well, I think I usually put the private section first. Private and public. So our private section is going to need to have access to nodes, right? Because we're going to have to keep track of the head of the list, tail of the list, and a count, is what I said. So since I need to have access to nodes, I need to include node.hpp. All right, so I'm going to have a node pointer called head, a node pointer called tail, and we'll say an int count. Those are going to be the three pieces of information that we keep track of inside of our linked list. Now in the public section, we're going to have our constructor. So this is going to be a linked list, take in no parameters. Let's just start with this and we'll start adding some functions. Okay, so now let's go ahead and let's write our linked list.cpp. And this guy will include linked list HPP. And then we're going to start implementing these things. So we have our linked list : linked list takes no parameters. And what this constructor is going to do is it's going to initialize the head, the tail, and the count. So this head is equal to null. This tail is equal to null. And this count is equal to 0. Okay, and let me just try something here. Namespace std. So null is not defined there. Is it in standard lib maybe? Yeah. So standard library, this guy right here is where this null value lives. So we need to include the standard library to give us access to nothingness. The reality is that in C++, the null value is actually just a 0. You can put a 0 there if you want, but null being a placeholder to it, null has a meaning to us. Null means the empty object, the empty memory location, where 0 says, well, is that a number? Is it being used for nothingness related to a memory address? So I would probably write it like this with null. And we need standard lib in order to do that. I'm going to go ahead and add it to my CPP file for node. Now he knows how to do the same thing. All right, so constructing a linked list involves initializing the original values. Okay, so now if we had a linked list to begin with, it's an empty list. A display method is probably going to show the empty list, right? So I'm going to go ahead back to linked list HPP. We're going to have a void display method here. So I'll prototype it there. We'll go over to linked list CPP. We'll go ahead and write this guy. And since we haven't written any abilities in yet for adding stuff to our list, we'll just ask a question in here. If this count is equal to 0, then we'll do something like cout the empty list. Something like that. So this should allow us to do kind of an end-to-end test of our starting point for our linked list here. So let's go into driver. I'll go ahead and comment out these couple of things that we're doing right now. We're going to go ahead and we're going to include our linked list HPP. And we'll go ahead and create a linked list pointer LL, as this is going to be a new linked list with no parameters. Then we'll say LL.display. We'll call that guy's display method, which should give us empty list. Which file? Driver CPP. Didn't I put the header up there? Include linked list HPP. These guys all saved. Go ahead.
So in the driver, you also need to put the CPP files?
Just the HPP files.
Okay, so how does it know to read what's up in the CPP files too?
Because the implement, I mean, when C++ does its linking, it follows the header file and goes and finds the implementation of it in one of your other files in the same directory.
Okay, so that happens automatically.
Happens automatically.
I wasn't sure about like all the things they have with the having the including that.
What is this guy complaining about? Oh, because of the cout. So this guy is not compiling correctly. So it doesn't know about this because it's not compiling the header file correctly, which then says, I can't find this header file that you've bragged about. So we need to include IOStream. And then this guy should be happy, which then means it should compile. Let's see. My files saved? All right, that guy looks happy. Am I doing anything funky in here? He looks happy. Just make sure that I have all my files in here. Oh, my compile is not compiling all the files right now. Right now, I'm just compiling driver CPP, URL CPP. So I need to add in. We really could just say star CPP for us right now. And I think that should cover things as we keep adding. So I'm saying compile all of the CPP files in this directory. Oh, when I was messing with the thing after class, last class, I was like, what's the problem here? Yeah, there's a debugger called DBG, and you have to compile it with a debugger flag so that the debugger can, at some point I'll show it to you. It's not a friendly debugger, it's all command line, but I just threw the -G. It's not gonna hurt anything. You can, it's not gonna hurt anything. It just kind of makes your, it adds extra things in the code so that the debugger can talk to it. Okay, so now it seems to be happy. I'll do a.out, and there's the empty list. Okay. All right, now, what's the next thing that we might want to do? We might want to add stuff to our list, right? Maybe add something to the end of the list. Let's start with that. Because right now I have a list, but my list has head and tail both pointing to nothingness because the list has no things in it, right? So now I want to be able to add something to the end of the list. So we'll go into our linked list, HPP. And we're going to go ahead and we're going to create a function called void add end. And we'll have this guy taking a value, the value we're going to add to the end of the list. Then we'll go and add this to our linked list CPP. All right, so now we want to add something to the end of the list. Now, where is the end of our list? What points to the end of our list? Tail. Tail always points to the end of the list. Now, right now, the end of our list and the beginning of our list are the same thing, and they're both equal to null, correct? We know that they both point to their, let me write the first line of code here. We're going to ask a question. We're going to say if head is equal to null, which is actually the same thing as just saying as not head. But we'll be explicit here. We're saying if head is equal to null, that means we have the empty list. Else, we have a list with at least one element in it, and we know that tail points to the end of that list. That's the assumption we're going to make there. All right. Any way you cut it, if I am adding a value here, I'm going to be adding a new node. So I'll say node pointer n is equal to a new node passing it value. Okay, so I'm going to create a new instance of node passing it my value. As a reminder, here's node CPP. My constructor expects me to receive a payload. It sets that node's payload and sets the next node to null. All right, so whether I'm dealing with the empty list or I'm dealing with a list with stuff in it, either way, I need to build a new node. Now I have my node. What do I do with the node? Well, if it's the empty list, then I want head and tail to point to this node. So this head is equal to n. This tail is equal to n. If it was the empty list, now it's the one list. Head and tail both point to the same place. Otherwise, I need to do a little hooking up. We go back here. Let's assume that my list looks like this 4, 6, 8 currently, and I'm adding 2 to the end. It's not the empty list, so I'm in that else. And we're going to say, okay, well, in order to tack this guy, this is n, right? I have my node pointer n, so that's this guy right here. In order to add him to the end of the list, I first need to go to the current tail and set that guy's next node to n. I need to make this guy aware of this guy. So I'll say tail set next node to n. I will make what tail currently points to point to the new node we're adding to the end. That makes sense? Then, and only then, because now I've had to connect this guy up. So now this guy is set up. So now I can make tail point to this guy rather than to the guy that it used to point to. So first make tail point to make the current tail point to the new guy, then make the tail pointer point to the guy that's now the new tail of the list. So tail is equal to n. So the old tail will get linked to n, then we'll set the new tail to be what n is. All right, any way you cut it here? Go ahead. Actually, you don't need to here, but I prefer to, so I'm glad you said that. You don't need to do it here because we are in a non-static context with that end, but I would always write it this way. It's much more explicit and I prefer it. So this linked lists tail. All right, now any way you cut it, whether we had the empty list we added something to, or we had a list with something in it that we added something to, count is now one bigger than it used to be. I've added something. So I'll say this count plus plus. All right, that makes sense? So now, let's go ahead and test this. So we'll go to driver. I created my linked list. I'll go ahead and say LL add end to add end 3. Actually, let's make it mimic this guy. So we had a 4, a 6, an 8, and a 2. So 4, 6, 8, 2. Okay, so I will add those guys to the end of my list. So I added a 4 to the end first, then I added a 6 after that, then an 8 after that, and a 2 after that. Now, what we hope happens here is we at least don't get any errors. But our display method, we haven't taught it what to do now if there are more than 0 elements. So this guy should still show me the empty list. Oh, it doesn't say the empty list because I asked the question if count is equal to 0. Count is not equal to 0, but I only do anything in here if count is equal to 0. That's when I only do anything if it's equal to 0. Right now it should be equal to 4. So we have to go and implement this else. What do we do if there is something in that list? Well, what we're going to do is we are going to traverse the list. We're going to start off pointing to the same thing that head points to. We do not want to change the head pointer because then we break our list. So we're going to have another variable that points to the same place that head points to, and then we can change that variable's value to walk through the list. We want to make sure that head always points to the beginning of the list and tail always points to the end of the list. Never change that unless you know what you're doing. If you want to walk through the list, you're going to, kind of throw your own little grappling hook there, holding on, and you'll visit that node, and then you'll toss it to the next one, visit that next node, so on and so forth. So we're going to go ahead and give ourselves a node pointer, maybe called CurNode, and we'll set this guy equal to the same thing head's equal to. So now CurNode and head both point to the same place in memory. All right, by this example, head points to this 4, and now I have this other variable maybe called CurNode, which also points to the place in memory where this 4 lives. Okay, Now, what I want to do is I want to ultimately display each node. So we're going to say while cur node get next node is not equal to null. So as long as the current node that I'm pointed at isn't the last node, what do I want to do? I want to go ahead and tell that guy to print its payload. So we'll say cout cur node get payload. And that'll get the value that lives in there. And then I'm going to put a little, we'll make it very link listy. Put a little arrow there so we'll actually see the link. And then after we do that, we're going to set cur node equal to his own next node. So cur node currently points here. Then the next time he's going to overwrite himself with his own next node. So now he'll point to the next guy. So by this picture, cur node will start off pointing here. Then it'll point to his own next node, which is here. Then he'll point to his own next node, which is here. Then he'll point to his own next node, which is here. But we'll finally fall out of that while loop when our next node is null. So right now, cur node currently points at this last guy. So we'll go ahead and this is where we'll kick it down the line in our code. So after this while loop is done, we'll do a final cout cur node get next node. And actually, I haven't finished this yet. This is also get payload. The get next node is a node object. I can print it, but it's just going to look like a memory address. I really want the payload that lives at this place. So there's cur node get payload, and then cur node is equal to cur node get next node. That walks me to the next node. But down here, when I output, I want cur node sorry, it's just get payload, not get next node. Because get next node when we're here is going to be a null. So we want to get the final cur node's next node, or cur node's payload rather. Get the final cur node's payload. And then output that. So now we're adding 4 elements to our linked list, and then we're calling display, which should show us, it should get into this else here. It should start cur node off pointing to the front of the list. And then as long as we keep having next nodes, we will go ahead and output cur node with a little arrow after it, his payload. And then we'll set cur node equal to his own next node. Traverse down the list until we finally get to the node that's at the end of the list. How do we know we're there? Because cur node's get next node is going to be equal to null. He does not have a next node anymore because he's at the end of the list. That's this picture right here. Go ahead.
Instead of having that, like, cur node dot next node equals null, which is equal null, could you have it so that cur node equal tail? Like
you could say, well, it doesn't equal tail, do this, and as soon as it's equal to tail, do something else. Yeah, but I mean, ultimately, it's the same thing. Yeah, but you're right.
And then what is that last cout cur node get payload after the while loop?
He'll actually print this too. Yep, so this will print this with an arrow, then this will print this with an arrow, then it'll print this with an arrow. And then at that point, I'm pointed here, this guy's next node is null. So I won't print this with an arrow. Instead, I'll fall out. I'll just print this with, and then kick it down the line. Because if you notice, I left end L off up here. So it's going to do this with an arrow, all on one line. So it should look, I don't know, awesome or whatever. All right, so we'll go compile this and then run it. And there's our linked list. And then if we're interested, and we would have seen this with something I had left in there before, when we output it, if I go into linked list CPP, if I don't say payload, I just say show me cur node, these will now be memory addresses. And what we're interested in here is to see that these guys are not necessarily right next to each other. They are not contiguous memory. Okay, this is giant hexadecimal number that isn't necessarily right next to this guy. This is E10, this is D50. Go ahead.
So then instead of cur node bracket, you just cur node 50%. Would that show you the thing that you don't have that many addresses?
So you want to do, what do you want to do? You want to say the address of cur node, like that? Well, no, because what is this guy? The address of cur node will give me what value? Or we'll put them right next to each other. It's kind of an interesting thing to look at. So we'll say address of cur node. Because somebody said maybe it'll be the same thing, right? Shouldn't be. I didn't put any spaces, but not the same thing, right? 0x7ff, 0x555. So why isn't this and that the same thing? What is this? This guy is giving me the value that lives in cur node, which is that's where the node lives in memory. What's this guy giving me? Exactly. Yep. So the ampersand here says, give me the address of this dude. Well, cur node is a variable. Where does cur node live in memory? That's what this guy is giving me. Okay. So cur node has a value. Cur node's value is a memory address which points to a node. But cur node itself is a variable. It lives itself somewhere in memory, right? So the address of cur node is not going to give me anything dealing with the contents of cur node. Instead, it's telling me, where can I find cur node? Where does he live in memory? Because the operating system somewhere carved out a little plot of land to hold that variable, the variable called cur node, which holds a value, which is a memory address, which points to a node. See, super easy. Now you see why pointers they are intimidating, but really they're just numbers, but they're intimidating because of this. They seem terrifying, right? Because they're those giant things that we can't read. They're just numbers. This is house 3, this is house 7, this is house 9, this is house 14, i.e. not next to each other.
So every time that you print it out, everything per node is the same each time. That's what it looks like.
Well, here, let me put a space in here just so I can read it more easily. And yes, it would be. And I'll explain why. So this value is the same as this value, is the same as this value. Why is that? Because we created cur node one time. This is a variable that got set equal to some that lives somewhere in memory. But this variable itself doesn't move around in memory. The value it holds, we change when we do something like this. We set cur node's contents equal to something else. But the location of cur node itself does not change. We created a variable right here, just like if I had int a. is equal to 5. And then inside here, I said A plus plus. I'm changing the value held in A. But A still lives somewhere in memory. Somewhere there's a little plot of land in memory that knows how to hold an int. And that's going to stay the same plot of land. And I can just keep putting as many, I can keep overwriting it with as many ints as I want, but it's still only one place. That make sense? So these two things are effectively doing the same thing as far as this goes. If we were to do a, instead of kernode, we would say the address of A. That is, where does A live in memory? Which should be also probably a different memory address, but it'll be the same memory address every single time. So there's that, there's that, there's that, same address every time. That's where the variable A was created and given a little home in memory. All right, that makes some sense? So we'll go back to just that. So this is our linked list where we're adding stuff to the end, right? Now, what if we want to remove stuff from the end? Let's compile it again, make sure we're back to where we were. Oh, I'm not doing the payload yet. Payload. Now we'll be back to our, oh, no, I'm lying. That's not where I put it. I put it here. That'll give me the value that lives there. All right, so there's the contents of my list. All right, so now the next thing we might want to do is maybe we want to remove from the end of the list. We've added to the end. Now maybe we remove from the end. All right, so that's going to require me going to where tail is and getting rid of that guy. But what does that mean? That means that tail is actually going to be the new last element in the list. So if I use this as the example, tail currently points here. That's the guy I'm going to remove. Usually we return the value as well. We'll say, hey, here's your 2 in case you want it. All right. But when all is said and done, we actually want tail to now point to 8. So in order to remove something from the end, we have to first walk our list until we get to the element right before tail. That is the element whose next node is equal to tail. This guy's next node points to the same place tail points to. All right. Now, if I'm dealing with the 1 list, that means we're getting rid of the one thing that's in there. There's no traversing up. So I can treat the 1 list as a special case. So let's go into our header file, and we're going to go ahead and we're going to say int remove end. And then we'll go ahead and implement it. Yeah, so like by this example out here, it would return a 2. If you wanted to use it, great. If you didn't, you could choose to have it return the node, but that's kind of a waste. I've disconnected it already. The node just has this payload in it in our case here. So now possibly in our Hearthstone example, well, Hearthstone, our node would probably hold a value whose payload was a Hearthstone card. But similarly, we could modify Hearthstone card to be the node itself, where you have a card linked to another card, linked to another card, rather than a card living in like a little container, which is linked to the next container, so on and so forth. Doesn't really matter, but typically we're using these nodes as just containers for holding our values. And when we actually remove something, we kind of just want the value that lived in there. All right, so here's remove end. So we'll just ask our first special case question. So if this count is equal to 1. If I have the 1 list here, then I'm going to go ahead and get rid of, we know right from the get-go, int value gets this tail get payload. That's the dude we're returning all day long, right? Now, for right now, we are assuming that there's at least something in this list. So really, we should probably do something like if this count is greater than 0, if there is something to remove, then we want to perform this logic. So if there is something to remove, no matter what this logic does inside of here, the value will ultimately return is the payload of the current tail. So I'll go ahead and throw that in a variable. If the count is 1, then what are we going to do? Well, that means there's one element, head and tail both point to the same thing. So I'm going to go ahead and I'm going to set head and tail both equal to null. So I'll set head gets the value null. And I'll say this dot. And this dot tail equals the value null. Now, right now, we are being poor stewards of memory. Because what we just did is, so I'll go ahead and finish this. We'll say return value down here at the end. And before we do that, we want to say this count minus minus. So if I'm dealing with the 1 list, what am I going to do? I'm just going to set head and tail to null, abandoning what used to be this node in memory, which I did preserve. I preserved its value. I said, hey, I'll just remember the number. Got the number, right? But the node itself is still out there in memory with nothing pointing to it. So head and tail, both of them used to point to that same place, right? But now they point to nothingness. But that thing, that node, is still in memory. Who's going to clean it up? Java had automatic garbage collection. C++ does not. Now, we got 8 gigs, 16 gigs, 32 gigs of RAM, whatever. Make a couple of messes, it'll dry. My wife does not like that, by the way. We figure if we make a mess, we should clean up the mess, okay? So we need to utilize a function called delete to give back memory. New gave us new memory. So new is how we asked for memory. Delete is how we give it back. So what I'm actually going to do is up here, I'm going to say node pointer value will be the same thing as tail points to. I'll make this guy point at the same thing tail points to. Then I'll break head and tails pointers and make them point nowhere, but I still have that last tail. So actually I'm going to call this node n. And then we're going to say int value is equal to n get payload. So now I've preserved a pointer to the node, and I've also preserved the value that lives there. Because before I exit this program, before I exit this method rather, I want to disconnect in memory. I want to give back to the operating system the memory that used to hold whatever n is. But I do ultimately want to return the value that lived in n, the payload, so I'll go ahead and preserve that. So then right here, I'll go ahead and say delete n. And that cleans up the mess. That lets the operating system know that, hey, here's this memory address. I'm not using it anymore. You can reclaim it. Hand it out to somebody else. Make sense? Not doing this, if we didn't do this, we technically have a memory leak. Probably heard that phrase before. Memory leak. It's when you were given memory and you abandoned it, not cleaning it up, which then technically means that your program has a bigger memory footprint than you're using, hence a memory leak. Go ahead.
So just to make sure, you have delete a memory address?
Yeah, we'll add it to a slide here. This is the opposite of the new keyword. This gives the operating system back memory you no longer need. Syntax is delete memory address. All right, so this is currently remove end if we only have a 1 count. Else, if there's at least 2 things in there, I need to walk up to the thing immediately before, but not including tail, right? So I'll say node pointer cur node is equal to this head. Then I'll say while cur node get next node is not equal to tail, cur node is equal to cur node get next node. So this will walk cur node down the list until I finally am in a situation where cur node's next node is tail. So now I'm positioned at the guy right before him. And what do I do if I'm the guy right before him? Well, that's the new tail, right? I've already preserved the value of tail up here. So I don't need to worry about that. So now I can say this tail is equal to cur node. That's what tail should now point to. And then I can also say this tail set next node to null. I'll actually disconnect it. Otherwise, he'll still point to that memory that we're about to delete. Okay, so I get to the guy right before tail. I set tail to point to him, and then I tell him to forget about the dude who's next door, because we're about to kill him off. Okay? So if I do this just real quick, I know we're almost out of time. I'll go back to driver. And we'll prove this is working. So we displayed everything, and we'll say remove end. And we'll say int value is equal to remove end. And then we'll say LL display. And then we'll say cout value and del. So we should get the 2 printed out there. And then we should get everything except the 2 after we removed printed out. So there's the full list. Then we remove the 2. There's the updated list. And then here's that 2 we removed, proving that we removed it. All right, that makes sense? So, homework. Add to our linked list implementation the following methods. add front, which adds a value to the front of the list. Remove front, which removes a value from the front of the list and returns its payload, like we did with remove end. Submit the GitHub link and the self-eval. Questions, comments, go ahead.
Would it be like more efficient to add something like have all of the nodes be able to point to the one behind them as well, and then you can walk it?
Yeah, you're calling that's a doubly linked list. We're talking about singly linked lists. So what he's asking about is, hey, wouldn't it be nice if a node didn't just know about the guy after him, but also knew about the previous node, which would then make it so that we didn't have to walk to the node right before. We could just ask a node, say, hey, who's the dude before you? Yes. More efficient, it depends on what we're trying to be efficient with. We're trying to be efficient with memory, or are we trying to be efficient with speed?
Would you say it's definitely more efficient to be like a previous line?
Well, it's definitely more efficient with speed because I can just get to a place and then get to the place before it. But with memory, I'm storing an extra variable, an extra memory address in each node. Who cares, probably? So realistically, the answer to your question is yes, it's more efficient. All right, I'll go ahead and push my current code up, and I'll put it up on, I'll put the assignment up on Blackboard. I'll see everybody on Tuesday. You came just for my class?
Yep.
Well, I'm totally worth it. Obviously.
I'm not asking questions when I'm online, and I ask more questions than everybody in class combined.
That's right. Well, that's good.
It just kind of works out when we get something. And I really don't want to stay till 3 for one more class.
What class do you have at 3?